Okay, so here's my video reassessment for standard number 2, atomic models. Yeah, just chose a problem from the homework. I'm most definitely going to end up doing another problem because as I look through the standard at the type of questions that it had, this problem doesn't really relate to the standard problem, but it was a chapter 37 homework problem, so it's definitely worth doing and going through. But I definitely plan on doing another problem. But anyway, getting right into the problem reads, a 2 centimeter diameter metal sphere is glowing red, but a spectrum shows that its emission spectrum peaks at an infrared wavelength of 2 micrometers. How much power does the sphere radiate? So basically, just to kind of give myself a visual, I just like to given information in the problem told me that it was a 2 centimeter diameter sphere, so that makes the radius 1 centimeter. All right, so basically what the question is asking me is it's asking me to find the power radiated by this sphere. It's this hot, glowing red sphere. So basically just breaking it down, just having to use some background information. Power is measured in watts. And basically watts, the units for watts is joules per second, which is just an energy over time. So basically just in the book, it gave you, it was really just backtracking on some stuff that it gave you earlier in the chapter, but it basically gave you this heat energy equation over a time interval, which we have here. It said that the heat energy radiated over a time interval is E, this little sigma symbol, A times the temperature to the fourth power, where E is the emissivity of the surface, basically how well the surface radiates, absorbs, and emits heat or energy. And for we said in the book that black bodies have an emissivity of 1. So basically, whatever it absorbs, it emits. And then, well, we also have this sigma symbol. That's Boltzmann constant. Boltzmann constant is 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth. A is the area of the surface, which is just the area of our sphere. And T is the temperature of the object in Kelvin, which we'll have to find later. So once again, all right, we just said earlier that the units of power is basically measured in watts, which is joule per second, which is basically just an energy over time. So that right there makes a red light go off that our heat energy equation, which is an energy over a time interval, is the power radiated by this sphere. Because as we said, power is energy over time, and therefore we have heat energy over time. So that's the power. Uh, we just defined E as our emissivity. The sigma symbol is Boltzmann constant. A, which is the area of the sphere. To calculate the area of a sphere, just 4 pi r squared. That's what I have here. 4 pi, it was given to me in centimeters. Had to convert that to meters, which is 0.01 meters squared. And therefore, we have the area of our sphere is 0.001257 meters squared. Okay, so therefore, the only thing left that we need to find out to calculate the power is the temperature, which isn't given in the problem, but it does give us the peak of the black body spectrum of the problem. And basically, from some background knowledge, we can use that peak, which is given to us in nanometers, to figure out the temperature in Kelvin. Because it gave us this equation saying the peak in nanometers is equal to 2.60 times 10 to the 6 nanometers Kelvin divided by temperature in Kelvin. Well, we could use that since we have the peak, we could use that to find the temperature in Kelvin, which I do here. The peak is given to you as 2 micrometers. So therefore, I had to convert that micrometers to nanometers in order to plug it into this equation. After doing so, I got that the temperature in Kelvin was 1450 Kelvin. So now I have everything I need to calculate the power. So power is basically equal to emissivity, which is 1, times Boltzmann constant, which is 5.67 times 10 to the negative 8, times the area, times the temperature in Kelvin to the fourth. As I can see, this is all cancels out because m squared cancels out, Kelvin to the fourth cancels out. Therefore, the only thing we have left is watts. Watts is obviously our measure of energy. So therefore, everything checks out, and that's it. All right, thank you.